Hello, in this video I would like to talk about momentum, which is amount of motion. Momentum is a vector quantity, often have variable p, and it is defined as mass times velocity. The reason why momentum is defined in such way is that when an object has greater mass, it is often thought to have greater quote-unquote motion. And when an object is traveling at a greater speed, then it is often thought that it has quote-unquote greater motion. So therefore, for defining a quantity that defines the amount of motion, physicists just say we're going to define momentum as mass times velocity. In my previous video on work and energy and on the problem set, I talked about the definition of force, how definition of force is actually change in momentum with respect to time, and using chain rule, this is actually mass times acceleration plus the rate of change of mass times velocity. So therefore, F equals ma if m is constant. Because if m is constant, then dm dt becomes 0 and this term just disappears. However, that is not always the case. So for example, let's think of a rocket in space, and this rocket is ejecting a fuel at a rate rho and traveling at a constant speed of v naught. Then the force from the engine equals to mass times change in velocity, in which this is 0, plus dm dt times v naught, which in this case would be rho times v naught. So therefore, the formal definition of force should be F equals to dp dt instead of F equals ma, but typically in our daily life, masses of an object are usually constant. Now, the reason that momentum is useful is that momentum is conserved. And this is when, if and only if, there are no external forces. What I mean by external force is that, for example, non-external force is force from an object, namely collision between two objects. However, external forces are forces not from an object, like for example, like gravity. There is no like object that is like physically pulling like an object down. So what I mean by that is if I have two masses and they're moving at v1 and negative v2, for example, negative because it is going to the opposite direction, then the total momentum of this system equals m1 v1 minus m2 v2. And then let's say the final velocity after their collision equals to negative v1 prime, and m2 is traveling at v2 prime. And the final momentum equals negative m1 v1 prime plus m2 v2 prime. Since assuming there are no external forces because they're on a horizontal plane, the initial total momentum equals to the final momentum. Therefore, these two quantities are conserved. Now, momentum isn't always conserved, and momentum isn't conserved if the external force is not 0. In this case, there is impulse on the motion, in which definition of impulse is change in momentum, and it is often denoted as vector j. So change in momentum, this equals to change in the quantity mv, and similar to product rule of taking derivative, this is roughly equal to change in mass times velocity plus mass times change in velocity. And if I express these terms in terms of time integral, this equals to the integral of dm dt times velocity dt plus integral of m dv dt with respect to time, because change in mass, this equals to the integral of dm dt with respect to time from fundamental theorem of calculus, and change in velocity, this is also integral of dv dt with respect to time, again from fundamental theorem of calculus. And if I express these two, and if I combine these two integrals, this becomes the integral from, of course there is a bound from t initial to t final, of dm dt times velocity plus mass times dv dt with respect to time. And this is the form of complete derivative of this quantity mass times velocity from product rule of taking derivative. And since mass times velocity equals to momentum, this equals to dp dt, and I've said that rate of change in momentum equals to the external force, in which therefore change in momentum equals to the time integral from t initial to t final of the external force dt. Now, for example, let's say there are two objects with the same mass of m, and they're moving towards each other at the same speed v naught. And if they are under free fall, then there's going to be the force of gravity exerted on the downward direction. So there will be mg applied this way and mg applied that way. And if I set the coordinate system such that the horizontal direction is x and the vertical direction as y, then the force along the x direction is 0, because if you look at the both of those forces, if I add these two forces up, then there are no x component to this force because this is vertical towards the x-axis. Therefore, the momentum along the x direction is conserved. And the momentum along the x direction, this equals to mv naught minus mv naught equal to 0. So therefore, if these two collide, whether elastically or inelastically, their total momentum is going to be the same. However, the force along the y direction is not 0. And in fact, if I add these two forces up, this equals to negative 2 mg, because I'm adding two force of gravities, in which this equals to negative 2 mg. So therefore, if I write the momentum of y with respect to time, this equals to the integral of 0 to t of f of y dt plus the initial momentum of along the y direction. And since there are no motion along the y direction, since the velocity along the y direction is 0, this is just simply 0, and plugging this value into this integral, this equals to the integral of minus 2 mg dt, which equals to negative 2 mgt. Now this means that momentum of these two objects, the total momentum, is going to increase along the negative y direction as time passes, in which this corresponds to our kinematics equation of where the velocity increasing linearly. Therefore, the momentum should also increase linearly with respect to time. So there are two main motions with respect to momentum. One is inelastic collision. This means two objects stick to each other. So on this system, let's say m1 is traveling at v1 and m2 is traveling at v2, and then m1 and m2 stick and travel at v final, let's say. Then since momentum is conserved because there are no external forces such as gravity, or let me say it again, the external forces are cancelled out because whenever there is gravity, there is going to be normal force that's going to cancel out the external force. The momentum is conserved, therefore m1 v1 plus m2 v2 should equal to m1 plus m2 v final. Therefore, solving for v final equals to m1 v1 plus m2 v2 over m1 plus m2. And the second type is elastic collision. And this is when energy is conserved. What I mean by energy, it is specifically kinetic energy, because whenever we think of momentum is conserved, we usually think there are no potential energies involved because there are no external forces, external conservative forces as well. So therefore, the two equations would be so for example, if m1 was initially traveling at velocity at v1 and m2 was traveling at v2, and then after their interaction, m1 travels at v1 prime and m2 travels at v2 prime, then my two equations of motion is first energy conservation, in which that is going to be 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. That is just kinetic energy of m1 plus kinetic energy of m2 is conserved regardless of whatever time I'm measuring these energies. And the second equation is change in momentum equals 0. Therefore, m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. Again, since momentum is conserved, total momentum before the collision and after collision is the same. Now, if I do the math for these two, then the overall conclusion is that v2 prime minus v1 prime equals v1 minus v2. What this means is that the final relative velocity of those two masses are equal to the initial relative velocity of those two masses. And from here, physicists defined a quantity called coefficient of restitution. And this coefficient is often denoted as alpha, and the definition of alpha is v2 prime minus v1 prime divided by v1 minus v2, which is just final relative velocity divided by initial relative velocity. So in terms of elastic collision, the coefficient of restitution equals to 1 because, as I said, the math turns out that the final and the initial relative velocities are the same. However, for inelastic collision, alpha equals to 0 because remember, the two masses are traveling at the same velocity, which means their relative velocity is going to be 0. Therefore, the numerator of this coefficient is going to be 0, therefore alpha is going to be 0. And for the rest, the other types of collision, the coefficient of restitution is going to be within the range between 0 and 1. One other application of momentum is that if I divide the total momentum by the total mass, that is going to be the velocity of center of mass. Now, before I talk in detail about this velocity of center of mass, let me define what center of mass is. So center of mass, often denoted as xcm for x center of mass, equals to the sum of individual masses and their position and divided by their total masses. So for example, let's say on this x-axis, there is m1 at position -1, and m2 at position 1, and m3 at position 2. Then the x center of mass is going to be -1 times m1 plus 1 times m2 plus 2 times m3, all divided by m1 plus m2 plus m3. And therefore, using this definition, v center of mass, which is going to be time derivative of x center of mass, is going to be sum of individual mass and their velocities divided by their whole mass, which is going to be the total momentum divided by the total mass. The reason that this is important is that, for example, if the total momentum was 0, that means the x center of mass is conserved. Now, there was a problem where, let's say, there is two masses of m1 and m2, and the mass of the rod is 0. And if this is standing vertically like this, and if this falls, the question is asking, what is the distance traveled by m1? Now, in this case, since the external force is 0, momentum is conserved. Now, when I say momentum is conserved, momentum along the horizontal direction is conserved because there are no external forces in the horizontal direction. There is gravity, but that is on the vertical direction, so in this case, we can ignore gravity. Now, from here, if I set this point as 0, then center of mass of this system should also be 0. Therefore, if I call this position x2 and that x1, then m1 x1 should equal to m2 x2, and x1 plus x2 should equal to the length of the rod. And using these two equations, I can solve for x1 for the distance traveled by m1. So I've prepared several questions about momentum from the recent F equals MA exam. And the first one is from year 2016, question 13. So the basic situation on the problem is that there is mass m1 traveling at speed v0 and mass m2 at rest. and it is given that m2 equals to some constant alpha times m1. After m1 and m2 collide, m1 travels at speed v1 and m2 travels at speed v2. And it is assumed that the collision is one-dimensional, which means m1 and m2 will collide and they won't diverge through like the y direction. They will only stay within the horizontal direction. And if the quantity R2 is defined as V2 over V0, the question is asking what is the range of R2? So before we even think about R2, first thing that we notice is that momentum is conserved. Therefore, I can claim that M1 V0 equals to M1 V1 plus M2 V2. And if I divide this whole expression with M1, then the equation becomes V1 equals to V1 plus alpha V2 because M2 equals to alpha times M1. Now, previously I said the coefficient of restitution, which is defined by final relative velocity divided by initial relative velocity, should equal to 1 if the collision is elastic, and 0 if collision is inelastic. Which means this quantity is bounded by a range between 1 and 0. And before I called it alpha, but since alpha is already defined, I'm going to define this quantity as beta. And beta in this case would be V2 minus V1 divided by V0 because final relative velocity would be V2 minus V1 and initial velocity is just going to be V0 in this case. And from here, this is bounded by 1 and 0. Now, because R2 is only defined by V2 and V0, we don't need this V1 quantity. And the method of getting rid of this V1 quantity is from here. If we solve for V1, we get V1 equals to V0 minus alpha V2. And if you plug it into this form to here, we get beta equals to V2 minus V0 plus alpha V2 over V0, which equals to 1 plus alpha times R2, because V2 over V0 is R2, minus 1. Therefore, we can claim that 1 plus alpha times R2 minus 1 is bounded between 0 and 1. And solving for R2, we first add 1 to this expression because there is this negative 1 constant there, which leads to 1 is equal or less than 1 plus alpha times R2, which is equal or less than 2. Thus, we can divide this by 1 plus alpha, and resulting in R is equal or greater than 1 plus alpha, and equal or less than 2 over 1 plus alpha. And looking back to the question, it looks like E is the answer that we got from our calculation. So the next question is question 21 from the same year. Now this one was similar to the question that I mentioned before while explaining the center of mass. So on this problem, there is mass of 3m attached to a rod of length L, and on top of the rod, the mass is equal to m. And it is thought that the rod is massless. If there are no frictions, and if this system is given a small nudge, this system will fall such that there's going to be 3m and there's going to be m lying on the floor. And the question is asking, what is the distance traveled by m? Now, since there are no friction, that means there are no horizontal external forces, which means the total momentum along the horizontal direction is constant or conserved. But since both systems are at rest, this horizontal momentum equals 0. Now, since I said the definition of V center of mass equal to momentum over the total mass, in this case, V center of mass is going to be 0. So therefore, the center of mass, which is along this axis, should not move. So in this case, if I call this position as 0, and call the position of 3m as x1 and m of x2, then since center of mass should be 0, my conclusion is that 3m times x1 should equal to m times x2, and therefore x2 equals to 3x1. But since x1 plus x2 should equal to the length of the rod equals L, if I plug in the value of x2 here, I get 4x1 equals L, therefore x1 equals 1/4 of an L. And while x1 is the position of 3m, the position of m in which we have to get is 3 times x1. Therefore, x2 equals to 3/4 of L. And looking at the answer, A would be the correct answer for this question. So the next question is from 2017 F equals MA, and this is a series of questions from question 20 to 22. So in this question, there is small m traveling at velocity v0, and this collides with big M, which stays at rest. And after the collision, I'm just going to say small m moves at speed v1 and big M moves at speed v2. And quantity F is the momentum of big M after the collision divided by momentum of small m before the collision. In this case, it would be big M v2 over small m v0. Question 20 is asking what should be the condition to have maximum fractional momentum transfer if the collision is completely inelastic. That's the key point. So collision is inelastic, and we're supposed to get the condition for F max. Now, if collision is inelastic, I said that means that two masses stick to each other, in which it is going to look like m traveling at v0, and then this small m and big M will stick and travel at some speed v final. In this case, this v final is going to be v2. So therefore, from conservation of momentum, as there are no external forces, small m v0 equals to m plus big M v final, or v2, and therefore v2 is going to be m v0 over m plus big M. If I plug this form of v2 into the equation for the momentum transfer, F is going to be big M times small m v0 over m plus M divided by m v0. And canceling out the m v0, I get this F equals to big M over small m plus big M. Now, in order to maximize the momentum transfer, I noticed that if m is negligible, this is going to approach 1, which is the greatest value of F. Therefore, I'm going to claim that m is much smaller than m, or small m over big M is going to be less than 1. Looking at the answer choice A would be the correct answer. Now, question 21 is similar to question 20, but in this case, the collision is perfectly elastic, which means the relative velocity is the same. What I mean by relative velocity is that final relative velocity in this case is v2 minus v1, and the initial relative velocity would be v0. So v2 minus v1 equals to v0. Now, since we don't want v1 because the fractional momentum transfer is a function of v2 and v0, I'm going to first solve v1. So v1 is going to be v2 minus v0. And also from conservation of momentum, small m v0 equals to small m v0 equals small m v1 plus big M v2. And plugging in this value of v1 to here, this equals to m times v2 minus v0 plus big M v2. And thus solving for v2 by moving this term to the left, I get 2m v0 equals to small m plus big M v2. Therefore, v2 equals to 2m v0 over m plus big M. Now, plugging in the value of v2 to F, which F was equal to big M v2 over small m v0, this equals to big M times 2m v0 over m plus big M divided by m v0. Canceling out the m v0, I get 2 times big M over m plus big M. Now, the question was asking which of the following is the maximum possible value of this momentum transfer. Since big M and M are positive value, in order for this to be maximum, small m should be negligible compared to m, such that the limit as m goes to 0 would become 2. So therefore f max equals 2, and among the answer choice, D matches our answer. And the final question for this set of 3 questions is that the fractional energy transfer, this time it is energy, not momentum transfer, is the absolute value of final kinetic energy of m divided by initial kinetic energy of m. And it is asking if the collision is perfectly elastic, then what is the condition for the energy transfer to be maximum? So I'm going to define gamma as the energy transfer, which in this case is going to be 1/2 big M v2 squared over 1/2 small m v naught squared, because that is the final kinetic energy of big M and that is the initial kinetic energy of small m. And canceling out the 1/2, this is big M v2 squared over small m v naught squared. Now, since the collision is elastic, the relative velocity is conserved, which means v2 minus v1 equals to v naught. And since momentum is also conserved, small m v naught equals to m v1 plus big M v2. Now, remember from the last problem that we used these 2 equations to come up with the conclusion that v2 equals to 2 m v naught over small m big M. We don't need to recalculate this because it's going to lead to the same result. Now, plugging this value into v2, I get gamma equals to big M times 4m squared v naught squared over m plus big M squared divided by m v naught squared. V naught squared can be cancelled, m can be cancelled, in which this leads to 4m big M over m plus m big M squared. Now, from here, I'm going to divide each term by, each the numerator and the denominator by m squared, in which this is going to be 4 times small m over big M over 1 plus small m over big M squared. Now, since small m over big M, this is a dimensionless constant, I'm going to call this x, in which gamma of x would be 4x over 1 plus x squared. And I'm supposed to get at what x would gamma be the maximum. Now, I'm going to use derivative of gamma with respect to x, because if gamma of x looks like this, and at this point at x equals x naught, the gamma is at maximum, then the derivative at this point is 0. So I'm going to set the derivative of gamma with respect to x as 0. And derivative of x of 4x over 1 plus x squared, I'm going to use the product rule, in which this would be 4 over 1 plus x squared, because I initially first took the derivative with respect to 4x. And then the latter half is going to be derivative with respect to 1 over 1 plus x squared, which in this case it would be 4x over 1 plus x cubed times minus 2. And this equals 0. So therefore, 4 over 1 plus x squared equals to 8x divided by 1 plus x cubed, in which canceling this off, I get 1 plus x equals to 2x, and therefore x equals 1, which means small m equals to big M. Looking at the question, C matches our answer. Now note that for this question, the latter half of the question is approached quantitatively. I used more of like math instead of physical qualitative intuition. However, it is very important to note that for previous questions for the momentum transfer, I use qualitative physical intuition that momentum is going to be conserved, and that is probably the most important key point to catch before solving this kind of question. Moving on. So next question is from 2018A, question number 3. In this case, there are 2 balls with same masses. I'm going to call them M. And one of the ball is moving at a certain speed and the other is at rest. And it is asking which of the following choices would not occur. So looking at the choice A, it says final momentum in the x direction equals the initial momentum of ball 1. This is true because after the collision, the first ball is going to move at v1 and then the second ball is going to move at v2. Regardless of that, there are no external forces that are exerted to these two balls. Therefore, mv0 equals to mv1 plus mv2, in which momentum is conserved. Looking at B, it says total kinetic energy after the collision equals initial kinetic energy of ball 1. This is not true, because this is only true if the collision is elastic. But on the question, it never says the collision is elastic, and therefore assuming that energy is conserved is a dangerous assumption. So I'm gonna first choose B for this question. But let's look at the other choices as well. Choice C, final momentum of the two ball in the y direction as to 0. This is also a part of conservation of momentum, because initially there is no movement along the y direction, and even if these two balls have collided and they have twisted in direction, their y component of their momentum should add up to 0, because initially there were no momentum along the y axis. And looking at answer choice D, final speed of the center of mass of the two ball equals to half of the initial speed of ball 1. As I mentioned previously, V center of mass equals to the momentum divided by m total. In this case, this is mv0 divided by m plus m, which is 1/2 v0. So we've proved that V center of mass equals to the half of the initial speed of ball 1, which is what D is saying. And E, ball can't both be at rest after the collision. This is definitely true, because the two balls have a total of non-zero momentum, in which at least one of those balls should be moving in order for momentum to be conserved. Now let's look at question from 2018B. So on question 3, the situation is that there is a 3 kilogram object moving at 40 meters per second, and there is a 2 kilogram object moving at 20 meter per second. And then these two will inelastically collide, which means they're going to stick into a 5 kilogram object and move at some velocity v. Since there are no external forces that is applied, momentum is conserved. Therefore, 3 kilogram times 40 meter per second plus 2 kilogram times 20 meter per second equals to 5 kilograms times v. Now this is 120 kilogram times meter per second. That is 40 kilogram meter per second. Adding these two, this is 160 kilogram times meter per second. Therefore, velocity equals 160 kilogram times meter per second divided by 5 kilograms, in which this becomes 32 meter per second. Now, since kinetic energy equals to 1/2 mv squared, the kinetic energy of this system would be 1/2 times 5 kilograms times 32 meter per second squared, in which if you plug this value into the calculator, this is 2560 joules, which is approximately 2600 joules. And looking at the question, it would be answered. The answer would be C, 2600. And the last question is question 9. In this problem, 3 kilogram ball is moving at 10 meter per second to the east, while 2 kilogram ball is moving at 15 meter per second to the west. And it is asking which of the following statement could be true of this collision. Now, one thing to notice is that the total momentum is 3 kilograms times 10 meter per second minus 2 kilograms times 15 meter per second, because those two are moving at opposite directions, in which this is 0. What this means is that since the question says these two objects collide elastically, after the collision, their speed will be maintained, but they will be moving at different directions. In other words, the 2 kilogram ball can be moving at this direction at 15 meter per second, and 3 kilogram ball can be moving at the opposite direction, but with the speed of 10 meter per second, because still momentum is conserved as well as energy is conserved, because the velocities of each of the objects are conserved. Looking at the answer choice, it looks like for E, 2 kilogram moves directly south at 15 meter per second. The direction doesn't really matter because the total momentum is 0, so therefore the 3 kilogram ball is going to move north, but the important point is that 2 kilogram ball is moving at 15 meter per second, in which that aligns with the initial condition. Therefore, E would be the answer for the last question.